The title of this presentation is A Comparison of Quantum and Multinomial Processing Tree Models of the Interference Effect. My name is Chris Fisher, and my co-authors are Lorraine Borghetti, Joseph Haupt, Leslie Blaha, and Christopher Stevens. An interference effect occurs when making a judgment changes the marginal probability of a subsequent decision compared to when no judgment is made. Formally, an interference effect occurs when the law of total probability is violated. The equation for the law of total probability is shown below for a simple case of deciding to attack and categorizing a person as good or bad. The law of total probability is illustrated with two Euler diagrams below. The large rectangles represent the entire set of possibilities. The inner rectangle on the left represents the probability of attacking in the case that only a decision is made. The Euler diagram on the right shows a case in which a judgment is made before the decision. The diagram is partitioned by G for good and B for bad. The green area is also partitioned into two parts: the intersection between A and G, and the intersection between A and B. According to the law of total probability, the sum of these two partitions must equal the green rectangle on the left. Broadly speaking, theoretical accounts fall into two categories: models based on classical probability theory and models based on quantum probability theory. Classical probability theory is the theory of probability most people are familiar with. Events are defined as subsets of a universal set and obey Boolean logic. Many of these models struggle to account for the interference effect because they are constrained by the law of total probability. Quantum probability is based on an alternative set of axioms which allows the violation of the total law of probability under some conditions. Events are defined as subspaces within a vector space. One distinguishing feature is that events may be compatible or incompatible. The joint distribution of compatible events can be obtained from the same set of basis vectors. Joint events can be evaluated simultaneously in this case. The joint distribution of incompatible events is not defined. Instead, joint events must be assessed sequentially using different sets of basis vectors in the same space. Previous research has shown that a quantum model can account for the interference effect, but two models based on classical probability theory cannot. These two models were a Markov process model and a signal detection model. One question that remains is whether it is possible to develop a model based on classical probability theory which can account for interference effects. Our goal was to develop a model based on CPT that can produce interference effects. The model we developed is a novel multinomial processing tree with three types of processes: a category judgment process, a category revision process, and a decision process. Our second goal was to compare the quantum model and the new MPT model in terms of the qualitative patterns of interference effects they can produce. The categorization decision paradigm is often used to study interference effects. On each trial, a face is presented and the subject decides whether to attack or withdraw. Faces belong to either a good category or a bad category. Faces in the good category tend to be friendly, whereas faces in the bad category tend to be hostile. Participants can use facial features as a cue for assigning faces to categories. We define a type G face as a face most likely to be in the good category, and a type B face as a face most likely to be in the bad category. In the extended paradigm, there are three conditions as shown in the table. In all conditions, probabilistic feedback is provided at the end of each trial. In the XD condition, the face and true category are provided. Participants only make a decision. In the CD condition, the true category is not given. Instead, participants categorize the face as good or bad before deciding whether to attack. In the D condition, the true category is not given. However, participants are only instructed to make a decision. Interference effects are assessed by comparing the marginal attack probabilities in the D condition to the marginal attack probabilities in the XD and CD conditions. The table below shows the empirical pattern of interference effects formed by condition and phase type. The interference effect in the XD condition has the same magnitude but opposite direction for the two phase types. The interference effect in the CD condition is challenging for many models because it's asymmetric. It is positive for B-type phases but absent for G-type phases. We will provide a very brief description of the quantum model called the Belief Action Entanglement Model, or BAE. In the BAE, features are defined in a four-dimensional Hilbert space. The four orthonormal basis vectors correspond to the four action and category combinations: attack good, withdraw good, attack bad, and withdraw bad. The BAE is a dynamical process model with the following parameters. J is a probability that a face is categorized into its most likely category. For example, a type G face being categorized as good. The BAE also has a utility function with four utility parameters mu, corresponding to the utility of attacking. The utility values depend on face type and category. The utility parameters for type G faces are constrained so that one is the negative of the other. The entanglement parameter gamma aligns beliefs and actions to be consistent with each other. The interference effect depends jointly on the values of the utility parameters and the entanglement parameter. The judgment revision model, or JRM, is a multinomial processing tree model and falls into the broad category of a classical probability model. The JRM has three types of processes. One, a category judgment process. Two, a category revision process in which the category is switched depending on certainty in the judgment. For example, the judgment is switched from good to bad if there's uncertainty in the initial judgment. And third, there is a decision process. Multinomial processing trees, or MPTs, describe how a series of latent states or processes map to categorical data. As shown on the right, MPTs can be represented as a tree in which nodes represent cognitive states or processes, branches represent transitions from one state to another, and parameters represent transition probabilities and have a cognitive interpretation. A path is a series of connected branches that terminates at a response node on the right. The probability of a path is the product of transition probabilities along the path. The probability of a response is given by the sum of path probabilities associated with a given response. The example on the right shows that the probability of responding yes is a mixture of retrieving a memory and responding yes, and failing to retrieve a memory and guessing yes. The JRM has three types of parameters corresponding to the three types of processes. The parameter A represents the probability of attacking a face. There are four A parameters because it depends on both face type and category. The parameter J represents the probability of categorizing a face into its most likely category. For example, categorizing a type G face into the good category. Parameter C is the probability of being certain in the first judgment and not revising it. 1 minus C is the probability of being uncertain in the judgment and revising it from bad to good or from good to bad. In total, the JRM consists of 12 trees. We will provide an example of a tree for the XD, CD, and D conditions. In the XD condition, the face and true category are presented to the participant. For this reason, the parameters J and C play no role. In total, there are 4 trees corresponding to the 4 combinations of face type and category. The example on the right shows the tree for a type B face in the bad category. The parameter A maps directly to the responses. In the CD condition, participants categorize the face before deciding whether to attack. There are 2 trees for the category judgment, 1 for each face type. In addition, there are 4 decision trees, 1 for each combination of face type and category. The first example is the tree for categorizing a type B face, which shows that the J parameter maps directly to the bad category. The second example is conditioned on type B face being categorized as bad. In this case, the category bad is switched to good with probability 1 minus C. This is reflected in the indices of parameter A. In the D condition, participants are only instructed to decide whether to attack the face. There is 1 tree for each face type. The tree on the right is for a type B face and contains the parameters J, C, and A. The model assumes an implicit categorization occurs. You may have noticed that the trees from the XD and CD conditions are subtrees in this larger tree. When C is equal in all conditions, the JRM can only produce interference effects in the XD condition. However, C can vary in some conditions if justification is provided. Our justification is as follows. Attack probability should be more extreme in the XD condition because the category is known with certainty. In other words, attack probability should be closer to 0 or 1. The table below shows that the attack probabilities are more extreme in all cases except for type B face in the good category, which is highlighted in red. For this reason, we allow C to be greater for type B faces in the good category and denote this as CK. As shown on the right, parameter space partitioning, or PSP, is a method for identifying regions of a model's parameter space that corresponds to a qualitative data pattern. With PSP, it is possible to identify the number of patterns a model can produce, which can be used as an index of flexibility. It is also possible to estimate the volume of regions to determine how typical a pattern is. In total, there are 81 possible interference effect patterns. An interference effect can be positive, negative, or absent, and there are 4 interference effects to consider, 1 for each face type and category combination. We consider a constrained and unconstrained version of the JRM and BAE to assess how the constraints affect the qualitative patterns the models can generate. The results indicate that the unconstrained BAE is the most flexible in terms of the number of patterns it can produce. However, this does not take into account how much volume is assigned to each pattern, which might be small. As an alternative, we use the Gini coefficient to measure dispersion of volume distributions, which ranges from 1 being the least flexible to 0 being the most flexible. Overall, the flexibility of the models is low, but the unconstrained BAE is the most flexible. The JRM can produce interference effect even though it's based on classical probability theory. Interference effects emerge from a combination of categorization, category revision, and decision processes. The JRM assumes that interference effects in the CD condition arise through variations in certainty across conditions. The JRM is more flexible than the BAE in terms of qualitative interference effect patterns. Also, the JRM does not generalize to other reward rate conditions as well, but this could be fixed by incorporating a utility function into its decision process. Thank you for your attention.